Have you noticed that everyone in cloud native networking seems to be talking about eBPF? Whether it's Kubernetes, observability platforms, security tools, or telecoms cloud infrastructure, eBPF keeps appearing in discussions. eBPF, which stands for Extended Berkeley Packet Filter, allows small programs to run safely inside the Linux kernel. The result is better networking, improved visibility into system behavior, stronger security, and higher performance. So while most users never see it, eBPF is becoming one of the key technologies powering modern cloud native network. To understand why eBPF matters, let's look at how Linux traditionally works. Applications run in what's called user space. Whenever an application needs access to networking, storage, or processing resources, it must communicate with the Linux kernel through system calls. The kernel acts as the central control point between applications and hardware. This model has worked well for decades, but as networks become larger and more complex, it starts to show some limitations. Traditionally, adding networking, monitoring, or security capabilities often requires extra software components. These might include kernel modules, monitoring agents, service meshes, sidecars, and additional networking layers. Each extra component introduces more complexity, more resource consumption, and more operational overhead. As cloud-native environments continue to grow, operators are looking for simpler and more efficient ways to gain visibility, improve performance, and enhance security. This is where eBPF comes in. Think of eBPF as a way to run small programs safely inside the Linux kernel. A developer writes an eBPF program, the kernel verifies that it's safe, and then loads it dynamically. The program can then react to specific events such as network packets arriving, system calls being executed, or applications accessing resources. Because these programs run close to where the activity happens, they can provide powerful insights and controls with very little overhead. For telecom engineers, eBPF is becoming increasingly important. It can improve observability by providing deep visibility into network traffic and system behavior. It can enhance security by detecting threats closer to the source. It can accelerate packet processing and traffic management, and it can help operators manage increasingly complex cloud-native environments more efficiently. This is why eBPF is gaining attention across telecom networks, data centers, and edge computing platforms. Today, many cloud-native networking platforms already use eBPF extensively. Projects such as Cilium and Hubble rely on eBPF to provide networking, security, and observability capabilities. In telecom environments, eBPF is increasingly relevant for Kubernetes platforms, service-based architectures, edge clouds, and telco cloud deployments. By running closer to kernel, eBPF can often achieve better performance with less overhead than traditional approaches. Looking ahead, eBPF could become even more important. Future 6G networks are expected to be highly cloud-native, AI-driven, distributed, and autonomous. These networks will require real-time observability, intelligent automation, enhanced security, and efficient traffic management. eBPF provides many of the building blocks needed to support these capabilities. While it is not a 6G technology itself, it could become an important enabler for future AI-native telecom networks. So the simple way to think about eBPF is this. It allows small, safe programs to run inside the Linux kernel, giving operators and applications better visibility, stronger security, and higher performance. That is why eBPF is becoming an increasingly important part of cloud-native telecom infrastructure, from today's 5G networks to future evolution towards 6G. If you would like a deeper dive into eBPF, let me know in the comments. Thanks for watching.